Hi everyone. I wanted to do an example of to illustrate how Lagrange multipliers work, where that formula for Lagrange multipliers comes from. So let's look at this problem. It says to minimize the function f of xy equals 3x plus 4y subject to the constraint x squared plus y squared equals 4. Okay, so this function, what we can do is we can think about the level curves of this function. So if we set this function equal to a constant and ask which values of x and y make that happen, those values of x, y form curves, and those are called the level curves. The curves that give constant values to the function. So if you look at that particular function, you'll see that these level curves are just straight diagonal lines. And so the level curves look something like this. So this is, along this line the function is constant, along this line the function is a different constant. Maybe along this line the function has value 0, maybe here it has a value 1, 2, 3, 4. If I move the other direction it's -1, -2. So these are the values of my functions along these curves. There are level curves in between here for values between 1 and 2, I just didn't graph them. And then we also have our constraint, x squared plus y squared equals 4. Well, we know what that is. That's a circle of radius 2. And so that makes, so let's just draw that here, right? Like this. That's our constraint, okay? So what we want to do is we want to investigate where on this circle, so subject to this constraint, where on this circle does this function have a maximum and a minimum? So let's just pick a point. Let's pick a point over here. And let's just take a look at that point. Could the maximum or minimum be there? Well, let's zoom in to this region over here and just take a closer look of what's going on. So zooming in, what we have here is we have the circle, the arc of the circle, we've chosen a point, and we have our level curves. This is the level curve corresponding to the value of the function equal to 1. And then we have other level curves nearby. We have maybe 0.9 and 0.8 and 0.7. And as I go to the right, I have 1.1 and 1.2. Okay? So let's ask the question, if I move along this curve in this direction, moving along the constraint curve, what's happening to the values of the function? Well, they're increasing, right? And they keep increasing. So because of that, because they just keep increasing as I move through this point can't be a minimum or a maximum. Can't be a maximum because I get bigger as I go over here. Can't be a minimum because I'm smaller if I go a little bit to the left. So this can't be a minimum or a maximum. Now let's take a look at another point. Suppose I took a point, say, right over here. Now what's happening? Let's zoom into this picture. In this picture, here's my here's the arc of my circle, right? And here's my point that I'm at. And the level curves look like this. Now, as I move along this curve, the values of the function, I see I'm crossing level curves, the values of the function are increasing. Right? This might be 1.8. This might be the level curve over here, 1.9. This is 2.0, maybe like this. If I move this way, the values of the function are increasing, increasing, and now all of a sudden, I'm going across the curves in the other. I'm crossing these level curves in the other direction, and so the values of the function are decreasing. So the values of the function were increasing. Now they're decreasing. So this must correspond to a max. Well, how do I formulate that mathematically? Well, if I look at the gradient vector for the level curves, we know that the gradient vector, the gradient of f, points orthogonally to the level curves. And the same thing, if I take the gradient of the constraint function, let's say my constraint function was called v, that's orthogonal to the constraint curve. What's happening right here? Well, right here, because the curves are parallel, the gradient vectors must be parallel as well. So here, the gradient vector for the level curves, grad f, is parallel to the gradient vector for the constraint curve. And so this is the idea of Lagrange multipliers. We want to find where the maxes or minimums occur, we find where these two vectors are parallel. So that's Lagrange multipliers. Lagrange multipliers. All right. What does multiplier mean? Well, these vectors are parallel. Well, that for two vectors to be parallel, it means that one is a constant multiple of the other one. So Lagrange multiple says that the gradient of f has to be a multiple of the gradient of v. And this guy here, that's my Lagrange. I keep spelling Lagrange wrong. I don't know why I keep doing that. It's because I'm talking at the same time. Lagrange multiplier. That's my Lagrange multiplier right there. It's the constant that I'd have to multiply one vector by to get the other one, and it illustrates the idea that these vectors must be parallel to one another. And that's where you look for maxes and mins. So let's go ahead and solve this problem using Lagrange multipliers and see what we get. So my original function was 3x plus 4y, so I have to take the gradient of that. My constraint is x squared plus y squared, so I have to take the gradient of that. All right? So my original function f, I changed from a capital F to a lowercase f. I guess I should have been using capital here. Let's go ahead and compute that. So the function was 3x plus 4y, so its gradient is 3, 4. V was x squared plus y squared, so its gradient is 2x, 2y. Now, let's use this equation. It says that the gradient of f is a multiple of the gradient of v, so 3 is k times 2x. 4 is k times 2y. And actually I have one more equation that I can throw into the mix here, and that is the constraint equation itself. X squared plus y squared equals 4. And this system of equations is what I need to solve to find that point over there. How do you solve it? Well, in this one, I think we can solve this first equation for k. All right, you can solve that one for k. Just divide both sides by 2x. You see that k equals 3 over 2x. And now we can plug that into this equation over here. So let's write that down below. So we'll take that second equation, put it down here. 4 equals 3 over 2x times 2y. All right. So that becomes 4 equals 3y over x. And let's go ahead and solve this for y. So let's multiply both sides by x. So I get, and then divide by 3. I get y equals 4x over 3. And the only equation we haven't used yet is this one. So let's take this and plug it into there. All right, so I get x squared plus, well, y squared is this. So 4x over 3 squared equals 4. That's just this equation, using that. X squared plus 16x squared over 9 equals 4. Well, let's get a common denominator. This is the same as 9x over 9. So that's that is 25 x squared over 9 equals 4. So what I'm getting here, if I multiply both sides by 9, divide by 25, I'm getting x squared equals 36 over 25. So in other words, x is plus or minus 6 over 5. Okay, well, how do I get back to y? Well, just look at this over here. If x is positive 6/5, y is 4/3 of that. 4/3 of 6/5 is 8/5, right? So one point that I get is 6/5, comma 8/5. But when x is negative 6 over 5, y is 4/3 of that, right? So that's negative 8/5. So when x is negative 6/5, y is negative 8/5. So these are my two solutions. These are the two solutions to my Lagrange multiplier problem. Now, what do they correspond to in the picture? Well, the 6/5, 8/5 is this point over here. And the negative 6/5, negative 8/5 is this point over here. To find out if it's a maximum or minimum, really you have to plug these into the original function. So we should look at this original function. If you plug these numbers in, you see that this is a relatively large value, whereas if you plug these things in, it's the negative of that. So this is the maximum occurs here, and the minimum occurs here.